Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar in Haryana. Today we will be talking on electronic spectra of diatomic molecules under the paper Atomic Molecular and Laser Spectroscopy. We will be able to learn in this module the Born-Oppenheimer Approximation, classification of electronic states, vibrational structure of electronic transitions. The Born-Oppenheimer approximation. Two or more atoms bind together to form a molecule in such a way that the total energy is lower than the sum of the energy of the constituents. The electrons of the inner shell of atoms forming molecules remain localized about each nucleus, though the valence electrons are distributed throughout the molecule, and charge distribution of these electrons provide the binding force. If psi is an eigenfunction of H, then H psi r is equal to E psi r, where this small r is electronic coordinate and capital R is internuclear distance. The coordinates of the electrons and nuclei cannot be separated out because of term involved in Coulombic interaction between electrons and nuclei. Born and Oppenheimer were able to show that an approximate solution of equation A can be obtained by first solving the equation for the electrons alone with nuclear fixed positions. Therefore, the operator Tn is neglected, assuming nuclear mass is infinite, and hence the potential Vnn is constant. The Hamiltonian He is equal to Te plus Vee plus Ven, and Schrodinger wave equation is He psi E rr is equal to E r psi E rr. However, Ven depends on the position of the nuclei. ER can be obtained for different values of internuclear distances from equation B. The potential energy can be obtained by adding Cnn to ER. So, Vr is equal to ER plus Vnn is equal to ER plus Z1 Z2 B E square upon 4 pi epsilon naught r. Here Z1 and Z2 are the atomic numbers of two nuclei 1 and 2 respectively. These bonds are ionic or covalent nature, and the force experienced by the electrons and nuclei is of comparable intensity. As the nuclei are about 2000 times heavier than the electrons, the motion of the nuclei is much slower than that of the electrons. Hence, it is assumed that nuclei occupy fixed position in the atom. The Hamiltonian for the molecule can be written as H is equal to Tn plus Te plus Vee plus Ven plus Vnn, where Tn is kinetic energy operator of all the nuclei, Te is kinetic energy operator for the electrons, and Ve is potential energy operator for Coulombic interaction between electron and electron, and Ven is potential energy operator for Coulombic attraction of all electrons and all nuclei, and Vnn is Coulombic repulsion between nucleus. The variation of E as a function of r provides a part of the potential field in which nuclei move, while Vnn provides the other part of this field. The Hamiltonian for the nuclear motion is Hn is equal to Tn plus Vnn plus Ee, and Schrodinger wave equation is Hn psi nr is equal to Tn plus Vnn plus En. Ee psi n is equal to En psi n r. Here psi n is a function of r only and represents the stationary state of the nuclei. The total wave function is psi is equal to psi E rr psi nr. The total energy E is given by E is equal to Ee plus En. The wave function psi n in a first approximation can be expressed as psi n is equal to psi nu psi r, where psi nu is the vibrational eigenfunction of a linear oscillator. Thus, to a first approximation, psi is equal to psi e psi nu psi r. The total energy E of the molecule apart from the translational energy is regarded as the sum of rotational energy ER, vibrational energy E nu, and the electronic energy EE. That is, E is equal to EE plus E nu plus ER, where EE is defined as the energy of the stable electronic state corresponding to the minimum of V. The minimum of lowest electronic state is chosen as 0 point of the energy scale. This choice differs from atom to atom. The total energy in terms of wave numbers is T is equal to E upon Sc is equal to EE upon Sc plus E nu upon Sc plus ER upon Sc is equal to Te plus G nu plus Fj. As the electrons move faster than nuclei, the nuclei feel the potential energy of the averaged electronic distribution. This forms the basis of Born-Oppenheimer approximation. However, this approximation breaks down if electronic energy spacings are not large compared to vibrational spacings. This breakdown results in a situation where time scales of nuclear and electronic motions are not separable, and it is not possible to separate nuclear and electronic energies. Classification of electronic states. In diatomic molecules, the electrons move in strong electrostatic field of nuclei that is considered to be cylindrically symmetric about the bond axis. The orbital angular momentum L precesses very rapidly about the direction of electrostatic field, and only axial component of L is a constant of motion. The axial component field is characterized by the quantum number ml, where ml is equal to L, L minus 1 and so on minus L. As the internuclear field of the electrical nature, therefore, energy is not changed by the exchange of ml to minus ml. The absolute value of ml is designated by the symbol lemma, and this lemma is equal to ml is equal to 0, 1, 2, 3 and so on up to L. The figure depicts the coupling of L about the electric field along the internuclear axis, producing the axial component lemma. The symbols for these states are shown in the table below. Corresponding to this lemma 0, 1, 2, 3, 4 etc., symbols of the states can be designated as sigma, pi, triangular shape delta, phi and lemma. All these states are doubly degenerate except sigma state because of symmetry of ml to minus ml. The individual electronic spins vectorially add up to produce integral or half integral spin quantum number depending on whether there is even or odd number of electrons. If total spin is s, then multiplicity is 2s plus 1. The multiplicity of the term is designated by a superscript. The term symbol for a state is written as this lemma 2s plus 1. For lemma greater than 0, the orbital motion of the electrons produces a magnetic field along the bond axis, and s precesses about the magnetic field direction. The value EE decreases as the nuclei approaches each other because the attraction between electrons and nuclei increases, and this is opposed by the repulsion between the two nuclei. There is an equilibrium bond length, that is, there will be a minimum distance at which these two balance. The energy rises sharply with the further decrease in the separation of nuclei. The electronic state is then a bound state. The curve representing the variation of EE plus VNN is referred to as the potential curve. And the potential energy curve for each electronic state of the molecule has a different shape. The minima of potential curve falls at different equilibrium internuclear distances. In case of stable states, the electronic state is unstable if the potential curve has no minimum. In obtaining potential energy curve, nuclear kinetic energy term is ignored. Thus, VR doesn't depend on the mass of the nuclei. If VR is found for a given molecule, it applies to all lengths within Born variation, as VR is same for hydrogen molecule, HD and D2 molecules which have same bond length within Born-Oppenheimer approximation. The eigenvalue of sigma square is equal to 1. Thus, the two eigenvalues of the sigma operator are plus 1 and minus 1. Then sigma psi e plus is equal to plus 1 psi e plus, sigma psi e minus is equal to minus 1 psi e minus. Psi e plus and psi e minus represent the eigenfunction of sigma with eigenvalues plus 1 and minus 1 respectively. The function psi plus remains unchanged while psi minus changes sign under reflection operation. The electronic states which are doubly degenerate, lemma is greater than 0, may be distinguished as plus or minus. For example, triangular shape plus and triangular shape minus, etc. The electronic states sigma is not degenerate but can still be classified as sigma plus or sigma minus. Homonuclear diatomic molecules also have inversion symmetry through the midpoint of the band, with the midpoint taken as the origin of the Cartesian coordinate system and upper inversion operation. xi, yi, zi2 minus xi minus yi minus zi of electronic function twice in succession gives the same electronic function. Then we can write iota square psi I is equal to plus 1 psi e. The eigenvalues of operator I are therefore plus 1 and minus 1. The wave function either remains unchanged or change sign under inversion. The wave function is called even or G, Garrett, if it remains unchanged upon inversion. On the other hand, if wave function changes its sign upon inversion, it is called odd or U, ungraded. These symbols G and U are written as subscript to the term values like sigma G, sigma U. There is Hund's rule 1. The interaction between nuclear rotation and electronic angular momentum is assumed to be weak and also weak spin orbit coupling. L and S precess independently about the bond axis in diatomic molecules. Along the bond direction of the projections of L and S, that is lemma and sigma respectively, add together to give omega, so that J is equal to R plus omega. The figure is self-explanatory to show the origin of omega. There is Hund's rule 2. It is assumed that coupling of S and lemma is weak. S couples to the nuclear rotational axis. The magnetic field is also weak and S doesn't precess about the bond axis. S remains fixed in space and lemma is added vectorally to I, giving a resultant angular momentum n, and n is equal to R plus lemma, and then n combined with S to give total angular momentum J, so that J is equal to n plus S. The quantized components ms of S about the magnetic field direction have value h cross ms. The quantum number ms is designated by the symbol sigma that takes the values s, s minus 1, s minus 2 and so on up to minus s. So, sigma can take 2s plus 1 values. There is no resultant magnetic field for the electronic state sigma corresponding to lemma is equal to 0, and hence ms is not defined. These states have only one component, whatever be the multiplicity. Further, spin orbit coupling can lift the degeneracy of 2s plus 1 lemma state. The symbol omega is used to designate the quantum number of z component of total angular momentum spin plus orbit in diatomic molecules if coupling between L and S is weak. The quantum number omega is written as a subscript to the term symbol. Thus, the term symbol is 2s plus 1 lemma sigma, with sigma is equal to lemma plus s, lemma plus s minus 1 up to lemma minus s. As an example, a triplet triangular shape state is split by spin orbit coupling into 3 doubly degenerate levels. The vector addition of lemma plus sigma producing the total electronic angular momentum omega is shown in the figure. Symmetry properties of electronic functions need to be considered along with quantum numbers sigma, lemma and omega. The reflection operator sigma acting twice in succession on electronic wave function must give the original wave function, so that sigma square psi e is equal to plus 1 psi e. Vibrational structure of electronic transition. The total energy E and term value T of the molecule are given by E is equal to EE plus E nu plus ER and T is equal to E upon Hc plus EE upon Hc plus E nu upon Hc plus E gamma by Hc is equal to Te plus G nu plus Fj. The wave number of spectral line for a transition from the upper electronic state T1 to lower electronic state 2 to T2 is nu is equal to T prime minus T double prime. We can write the electronic state T1 to T prime or T2 to as T double prime. So nu is equal to T prime minus T double prime is equal to Te prime minus Te double prime plus G prime minus G double prime plus F prime minus F double prime. So that nu is equal to nu E plus nu plus nu R. For a given electronic transition, nu E is constant and corresponds to energy difference in wave numbers between the minima of the upper and lower electronic states. In case the rotational structure is ignored, putting the value of nu R is equal to 0, one gets nu is equal to nu E plus nu plus nu E plus G prime nu minus G double prime nu. And using the values of G prime nu and G double prime nu, one can write down G nu is equal to omega E nu plus 1 by 2 minus omega E Xc nu plus 1 by 2 square and so on. So that nu is equal to nu E plus, we just need to put the values of G nu to get the complete equation. The spectral location corresponds to J is equal to 0 to J is equal to 0 rotational transitions. In electronic transition, there are no strict selection rules on nu and it may take any positive or negative integer. For nu is equal to 0 to nu is equal to 0 transition, that means nu 0 0 is equal to nu E plus G prime 0 minus G double prime 0. So nu 0 0 is equal to nu E plus, writing the value of G prime 0 and G double prime 0 using the above relationship. So putting the values of omega 0 is equal to omega E is equal to omega E Xc plus 3 by 4 omega E Ye and omega naught x naught is equal to omega E Xc minus 3 by 2 omega E Ye and omega E Y0 is equal to omega E Ye. The vibrational levels measured relative to the nu is equal to 0 level in each state. So simplifying this, nu is equal to nu 0 0 plus G naught prime nu prime minus G naught double prime nu double prime. Conclusively, in case of diatomic molecules, S, sigma, lemma and omega adequately represent the quantized electronic angular momentum. In an isolated molecule, however, the total angular momentum is due to vectorial coupling of nuclear angular momentum I, electronic spin angular momentum S and electronic orbital angular momentum L. The figure also depicts a set of vibrational energy levels associated with two electronic states. The vibrational transitions accompanying an electronic transition are called vibronic transitions and are further divided into progressions and sequences. A progression involves a series of vibronic transitions with a common lower or upper level. As is seen in the figure, for the nu double prime progression members, nu prime is equal to 3 level is common, and for nu prime is equal to 0 progression members, all have nu double prime is equal to 0 level common, with nu prime is equal to 0, 1, 2, 3 4, etc. A new double prime progression extends towards the lower wave number as new double prime increases and terminates in a continuum where the lower electronic state dissociates. A new prime progression extends towards higher wave number as new prime increases and terminates in a continuum where the upper electronic state dissociates. A group of transitions with the same value of delta nu is referred to as a sequence. Long sequences are observed mostly in emission due to population requirements. The figure depicts that we get the progression and sequences, and the progressions and sequences are not mutually exclusive. Each member of a sequence is also a member of two progressions. The members of the progressions are widely spaced with approximate separation of omega e double prime in emission and omega e prime in absorption. Members of the sequence are closely spaced with approximate separation equal to omega e double prime minus omega e prime, as omega e double prime and omega e prime have slightly different values for the combining states. The bands in each sequence are generally found to be grouped together and overlap each other partially in the spectrum. Summarizing what we have learnt in this model, as the electrons move faster than nuclei, the nuclei feel the potential energy of the averaged electronic distribution. This forms the basis of Born-Oppenheimer approximation. However, this approximation breaks down if electronic energy spacing are not large compared to vibrational spacing. The vibrational transitions accompanying an electronic transition are called vibronic transitions and are further divided into progressions and sequences. The bands in each sequence are generally found to be grouped together and overlap each other partially in the spectrum. Thank you.